Welcome to the Explainer, everyone. Today, we are literally putting on our detective hats to solve a chemical mystery. We're going to determine the hidden concentration of a base by using a highly reliable standard acid. It sounds like standard chemistry, right? But when you look at it closely, it really plays out like a perfectly executed investigation. We've got our unknown suspect, our reliable informant, and a series of clues that will lead us exactly to the answer.
Okay, let's quickly map out this investigation. We're going to cover the mystery of titration, equipping the lab, the step-by-step neutralization, analyzing our data, and finally, cracking the concentration.
Starting right off with Part 1, the mystery of titration and understanding neutralization.
So to kick things off, we really need to understand the fundamental forces at play here. An acid-base titration isn't just blindly mixing liquids together. It is a highly controlled reaction, which brings us to the big question we're answering today. How exactly do scientists measure the invisible? Think about it. We are looking at a solution of sodium hydroxide, NaOH. But since we obviously can't zoom in and count the individual molecules floating around in that beaker, how do we confidently and accurately measure their concentration? Well, we do it by observing how they behave when they react with something we do know.
And that brings us to an absolutely crucial concept, the equivalence point. This is the exact moment during a titration when the moles of our acid perfectly equal the moles of our base. It's literally the precise second our chemical scales balance perfectly, meaning our neutralization is 100% complete. Finding that exact split second, that is the entire goal of our physical experiment.
Let's take a look at our two main characters. On one side, we have sodium hydroxide. It's a strong base, but here's the catch. In this scenario, it's a secondary standard. That means its concentration naturally fluctuates over time, so we just cannot trust it on its own. To interrogate it and find its true concentration, we are bringing in our reliable informant, a weak but highly standardized acid known as oxalic acid. Because oxalic acid is a primary standard, it's super stable and totally reliable. We know its exact molarity, in this case 0.050 molar. We are basically going to pit them against each other.
Moving on to Part 2, equipping the chemistry lab with the tools of the trade.
You know, every good detective needs their gear. And in chemistry, precision is everything. To pull off this neutralization safely and accurately, we'll need some specialized tools. A conical flask to house the reaction, a pipette and pipette pump to precisely measure our acid, and a burette to control the incredibly slow release of our base. But pay special attention to the last item on this list, phenolphthalein. That is our visual informant in this case. Without it, the reaction would be completely invisible to the naked eye.
Now, before we even think about interrogating the unknown base, we have to prep our reliable informant. We carefully synthesize our standard solution by taking exactly 0.63 grams of pure crystalline oxalic acid dihydrate and dissolving it into a volumetric flask containing exactly 100 milliliters of distilled water. This meticulous prep work is exactly what guarantees our acid is precisely 0.050 molar. I mean, if we mess this up, the whole investigation is compromised from the start.
Okay, let's get into Part 3, step-by-step neutralization, our working procedure.
So, the interrogation begins. Step 1, we fill the tall burette with our unknown sodium hydroxide. Step 2, we use our pipette to place exactly 10 milliliters of our known oxalic acid informant into the conical flask below. Step 3, we add just 1 or 2 drops of that phenolphthalein indicator to the flask. And finally, Step 4, we slowly, and I mean slowly, drip the base from the burette into the flask, swirling constantly, just waiting for that critical visual clue.
This right here brilliantly illustrates the climax of our lab work. Imagine you're swirling this clear liquid, adding base drop by drop, and then suddenly, boom! The instant that solution shifts from colorless to a faint, persistent pink, the phenolphthalein alarm bell rings. That color change is basically the molecules yelling, "Stop! You've hit the equivalence point. The neutralization is totally done." We stop the burette immediately and record exactly how much liquid we used.
Which brings us to Part 4, analyzing the chemical data at our evidence board.
With the physical experiment wrapped up, we take off our lab coats, sit down, and analyze the raw data. Actually, to make sure we were super accurate, we repeated that whole titration process 3 times to get a reliable average. So, looking at our data sheet, we started the burette with an initial reading of 12.9 milliliters. Once the liquid turned pink, we stopped and took our final reading, 23.4 milliliters. By subtracting the initial from the final, we deduced the difference. It took exactly 10.5 milliliters of our unknown sodium hydroxide to neutralize the 10 milliliters of our standard acid. We averaged this out across our trials, confirming that 10.5 milliliters is for sure our golden number.
But hold on, before we jump into the final math, we have to consult the chemical rule book, the reaction equation itself. Look closely at the reactants. We have oxalic acid, HOCCOOH, reacting with NaOH. The absolute vital clue here is the ratio. Notice the 2 right in front of the NaOH? That tells us it takes exactly 2 moles of sodium hydroxide to neutralize just 1 mole of our oxalic acid. They do not react on a simple 1-to-1 basis, and that stoichiometric ratio is the final piece of evidence we need to crack the case.
And finally, part 5, cracking the unknown concentration, our final deduction.
All right, we have all the pieces to our puzzle, so it's time to plug our evidence into the master formula. Because of that 2-to-1 ratio we just discovered, our standard titration formula gets a slight tweak. It becomes 2 times M1V1 equals M2V2. So let's plug in our knowns. We've got 2 times the molarity of our acid, which is 0.050, times the volume of our acid, which was 10 milliliters. We set all of that equal to M2, our unknown base's molarity, times our experimentally observed 10.5 milliliter volume.
From here, it's just simple algebra. We multiply the left side, divide by 10.5, and when we solve for M2, we definitively crack the mystery. The math proves it. The exact concentration of our previously unknown sodium hydroxide solution is 0.09 molar. By meticulously using a known standard and watching for that equivalence point, we literally made the invisible visible, and we put a precise number on an unknown suspect.
As we wrap up this explainer, I'm going to leave you with the final mystery from the source material to investigate on your own. We used a very specific chemical alarm bell for this experiment, but think about this. Considering we matched a strong base, NaOH, with a weak acid, oxalic acid, why was phenolphthalein the absolute perfect visual indicator for this specific case? What is it about its pH range that makes it the ideal choice over something else, like methyl orange? I highly encourage you to dig into that chemical property next. Thank you so much for joining me on this investigation, and keep exploring the fascinating, invisible structures of the world around us.